Thank you for the introduction. Good morning, everyone. My name is Wojciech Żuławiński, and the topic of my presentation is indeed applications of robust statistics for periodicity detection and non-Gaussian signals, the analysis in deep frequency domain. And this is a joint work with Professor Jérôme Antoni from INSA Lyon, Professor Radosław Żuławiński and Professor Agnieszka Romańska from Wrocław University of Science and Technology. And this is an example of our cooperation, as Professor Romańska mentioned, with our cooperation with the mining industry to solve the particular engineering problems. Here, devoted to the local damage detection as a periodicity detection problem. Here is the short agenda of the presentation. After the short introduction, I will present the considered here robust estimators of autocorrelation function, and then I will turn to the main point of the presentation, which are the robust spectral coherence maps. So the tool that we are using here to solve the problem of periodicity detection in non-Gaussian settings. And then I will present the application of this method to simulate and read signals to show how does it work. And of course, at the end, the summary. Okay, so many local damage detection procedures, for example, in the mining industry, as I mentioned, are based on the periodicity detection. So we assume that if there is a hidden periodicity present in a signal, this might be connected with the occurrence of the damage in the considered machine, for example. So let's say here the periodicity detection task is used here to solve the local damage detection problems. And many of such procedures are based on the autocorrelation function and standard estimators, so the sample ACF. But classical methods may fail if the signal under consideration has some heavy-weight non-Gaussian behavior. In such cases, as we will see also later, the classical methodologies tend to be inefficient. So that's why we need to think about some alternative solutions. And here we came up with the idea to propose very simple idea, just to propose the application of robust ACF estimators in periodicity detection algorithms. And here the algorithm under consideration is the spectral coherence map, which is a very well-known tool in the classical settings. But in the classical version, it is very sensitive to outliers. But here we propose the robust modification of this method. So using robust autocorrelation function estimators applied to these maps. That's our proposed solution to this problem. And as I mentioned, we will present the application of this methodology to some signals. This is one plot for the motivation of the whole problem, because here we can see that indeed the sample ACF estimator tends to be inefficient in a setups with outliers occurring in a signal. Because at the top of the slide we have some, let's say, signal, the standard signal, some sample trajectory of autoregressive model, no outliers yet, and here we have indeed some comparison between standard and robust ACF estimator, and comparison with the theoretical values of the ACF of such time series, which is of course well known. That's why we are able to compare it. And here everything is fine. But if we just take this sample and add some artificial outliers to it, like at the bottom bottom left plot. So here we change only a few observations out of the whole time series. Here and the rest of the sample is unchanged. So here we see that we lost the information about the dependence present in the signal, because we changed only a few observations, and that influenced that much the calculation of the standard autocorrelation function estimator. Yet the robust version is able to preserve the information about the dependence present in the signal, which is still occurring here. So that's why we proceed with considering the robust estimators for some algorithms in future slides. Okay, so which robust estimators do we consider here? First, we start with just to remind the non-robust, the classical sample ACF, which is given here at the top of the slide. And this is, as I mentioned, the non-robust version. So the algorithms based on this measure will tend to fail in the presence of heavy-weight non-Gaussian noise. So which estimators we are considering here to replace? The first one is the trimmed estimator. So it is a very simple modification of the standard estimator, because of course the autocovariance could be considered as an estimation of some expectation, so mean. So using the trimmed estimator, we just use here the trimmed mean, which is one of the possibilities to, let's say, robustify our statistic. here we are doing this for the purpose of the autocorrelation calculation. So this is the first of the proposed estimators. And we will be considering two more, which are related to some other measures of dependence other than the classical Pearson correlation. So Kendall, Tau, and Spearman-Roth correlations. And of course, by themselves, these measures are related to other measures of dependence. But here we are using them because using these transformation in the boxes present on the slide, we are able to, under some assumptions, we are able to translate the result of both Kendall and Spearman correlations to the language of Pearson correlation, to some sense. Yet we are using the, let's say, nice robust properties of both of these measures. So as both are sign or rank statistics, they tend to be more robust than the standard measures. So these estimators, these three robust estimators will be the ones that are be using in the, let's say, in the further work. But of course, we don't have to limit ourselves to only these ones. This methodology is general enough to consider as other measures. These three here are serve only as an example of the application. Okay, and we'll be using later the alpha stable distributions as the underlying distribution for our models to simulate the, let's say, cyclic signal with non-Gaussian behavior. So few information about it. So this is the definition of the symmetric alpha stable distribution based on its characteristic function. And of course, as we are aware of this fact, for alpha less than 2, this signal has the infinite variance. So the autocorrelation doesn't exist at all. It's not defined well. Yet we still use the robust estimators, just let's say to check if these approaches will indeed work even in such setup. And it turns out that they do. And of course, I just want to mention also the other approach, which is not considered here as a novelty, but it's taken to comparisons with our robust methodologies. So the methodology based on the normalized covariation measure of dependence. This is one of the measures of dependence defined, well defined for alpha stable distributions. So this is also some form of some ratio of expectations. And this was also mentioned by Professor Żuławińska. One of the methods that she was presenting was based on this measure, and we will be using it to compare with our results. Okay, so let us now turn to the robust spectral coherence map. This is the algorithm to calculate them. I will not go into many details because of the lack of time here, but I just want to point out here one very important thing, that what we are doing here is only changing one step of this algorithm. So in this red underlined line, this is the, let's say, step when we are calculating the autocorrelation function in the standard algorithm. Our, let's say, idea here is to simply replace this step with the calculation of selected robust autocorrelation function. We will be using all of the three estimators that I presented before. So this is only slight change in the algorithm. Yes, yet as you will see, such a change will result in very, very different result, and in consequence, the better result for such setup. And not going into much details, but this is some sort of a technical slide, because at this step of the algorithm, when we calculate the autocorrelation, we are doing it on the complex inputs, which might be a problem for so robust statistics in the standard form. So this is how we, let's say, do some workaround here to solve this problem and be able to apply these robust measures. So for trim statistic, as mentioned in the first bullet, we use such an equation, which, let's say, allows us to use the trimmed mean to estimate each of these four expectations as a trimmed mean problem. All of these four are now completely real, so we are able to apply the trimmed mean in the standard sense. For the Kendall-based estimator, there is not a problem, because we can use just the definition of the signum function also for complex inputs, so as presented here. And for the Spearman estimator, we also do some workaround by separately ranking the real and imaginary parts of both vectors that we are applying the Spearman estimator to, and we can just apply such ranked versions of these complex variables to, let's say, to calculate the Spearman estimator further. Okay, so which signals we are now going to use to compare our methodologies with the previously known ones? The first signal comes from is truly simulated, comes from the model presented here on the slide. So we have such a process xt, which is a sum of the deterministic component st, which are these cyclic impulses, and these cyclic impulses are related in practice to the occurrence of the damage. So these are the impulses which let's say, are corresponding to the presence of the damage in the machine. And this is how we, let's say, introduce it in our model. And the structure of of these impulses are such that the cyclic frequency is 30 hertz, so they occur in 30 times per second, these impulses. And what's also important is the informative frequency band in this range, which means that because each impulse is, let's say, has some form of decaying sign. So the structure of a single impulse is, let's say, the frequency structure of each impulse comes from this band. And this is the first term, so the cyclic impulses, and to this sequence of cyclic impulses, we add the ZT noise, which is the non-Gaussian noise. Here it comes from the alpha stable distribution with alpha parameter 1.7, so pretty non-Gaussian, I would say. And this is this non-Gaussian noise, which let's say covers the presence of cyclic impulses, as we will see in the plot of such a signal. And here we also consider the results will not be presented here, but they are very similar to the ones that I will present later. I just wanted to mention that here we also considered other distributions of this ZT noise. So Gaussian plus additive outliers, where so this ZT was a Gaussian distribution, but once we sometimes added also some outlying observations just to make the behavior of this noise impulsive. And we also consider the student T distribution with the infinite variance setup. So for numbers of degrees of freedom less than 2. And the second signal, this is the real vibration signal. So now we come to the real data, but it comes from a crashing machine, but this crashing machine was healthy. So in, let's say, the pure signal, the gathered signal, the periodicity was not detected because there wasn't a damage present here. So that's why it's not visible here. Oh, sorry. Okay, it's not that important. Okay. Okay, that's one thing. So to, let's say, make this signal also periodic in some sense, we added the same manner as before this ST cyclic impulse sequence with some amplitude just to introduce the periodicity to the signal. But let's say the background noise is completely real. It comes from the real crashing machine. And both of these signals consist of 50,000 observations, which corresponds to 2 seconds of the signal. And this is the plot for the first signal, so the one purely simulated with heavy non-Gaussian alpha stable noise. And what we can see here is that indeed there are many outlying values present in the signal, which completely cover the cyclic impulses present somewhere here. They are barely visible, which I'm sorry for, but let's say this makes the whole task much more difficult because of these outlying values present here. And we have also the spectrogram of this signal. Sometimes on the spectrogram, we are able to detect the periodicity by themselves, and we don't have to use other methods, but here it's not possible because of this heavy tail behavior of these outlying observations in consequence. And this is the plot of the second signal, and here we can more clearly see that this cyclic impulses sequence is very hidden in this background noise. So just by inspecting the time series, the signal looking at time series is very hard to distinguish and to detect the periodicity. Yet, as we will see later, there are some algorithms that are able to do it. Here we don't have such extreme outlying values as before, but still we have some coming from some specific processes conducted by a machine. And as we will see later, they also have strong influence on the results for the standard methodology, let's say. Okay, so these are the results of the spectral coherence maps for the first map, for the first signal, I'm sorry. And we compare here the spectral coherence maps based on different estimators on different measures of dependence. So here we have the result for the standard spectral coherence map based on the sample autocovariance autocorrelation estimator. Here we have the example, the map present for the this normalized covariation measure, so defined for the alpha stable particularly. And these four are for corresponding robust estimators for two different levels of trimming for the trimmed estimator. And what we can see here, what we should expect, first of all. First of all, we should expect that we only obtain the significant non-zero values for the true value of cyclic frequency, which was 30 hertz, and its multiples, so 60 and 90. So these are the areas that we expect, that we should expect only the significant values. And what's also important here is this mentioned by me before, the informative frequency band. So we should expect these values not only in this 30, 60, 90 x-axis frequency, let's say, but also for this only in this band marked by these red lines, which is the true informative frequency band of the simulated signal. And what we are seeing here is that this is indeed the case for the robust estimators present here, because in all of these four methods, the only values, significant ones that we are able to see are, let's say, the desired ones. And in comparison, let us look at the, let's say, standard map, the non-robust one, the classical one, where it is not the case, because it is very, very disturbed, and we are not able to properly detect the periodicity present in the signal. This is just too disturbed by, and this is directly influenced by the outlying values presence. And here we also have this this measure of dependence based defined for the alpha stable distribution. And here we are able to see something, but still it is much more disturbed by the results obtained for the robust estimators. So here we are clearly able to assess the results in such a way that the robust measures tend to be more efficient here. And this is the first signal, and this is the second signal. And because there is not such a large number of large outlying values, the results obtained for the standard map are not that bad as before, yet still, because here we are able to see anything in the desired areas, let's say. But still, these disturbances for engineers are, let's say, make this map disqualified, yes, because these are too significant and they don't bring the relevant information to consider them to be efficient. And in comparison, the robust maps, all of them were able to, let's say, preserve to provide the correct information about the periodicity without the significant disturbances in the background. Okay, so this was only the visual inspection of the map, yet we would also have, we would like to have a way to quantify the performance of the map, and we here using it, we are doing it using the amplitude ratio and the following indicator. This amplitude ratio is calculated for each epsilon, so for each x-axis frequency, and this is just the mean value for given epsilon frequency, mean value of the values obtained in the true informative frequency band for given epsilon, divided by the mean value of the whole map. And this is a statistic calculated for each epsilon. And the idea is, because we will present the plots against this epsilon frequency, the idea is here that for cyclic frequency, so for these 30, 60, and 90, the result should be as large as possible. And for the other frequencies, so for these non-cyclic ones, it should be as low as possible. So to further quantify this interpretation of the statistic, we consider here the following indicator of the efficiency of a single map, and just to be able to compare between the different maps. So here in the numerator, we have the values of this amplitude ratio calculated for the cyclic frequencies, so for these 30, 60, and 90 hertz, and we divided it by the sum of all computed values. And this is the statistics from the range 0 to 1. Of course, the larger, the better. And we will be presenting the results for different setups to compare the maps between themselves. Okay, so these are the plots of these amplitude ratios for the first signal. And as I mentioned here, the red dashed lines represent the true cyclic frequencies, so these 30, 60, and 90 hertz. And these are the areas that we expect our statistics to be as large as possible, and for the others to be as low as possible, as I mentioned. And indeed, this is the behavior observed for all robust methods. Yet, for example, in the standard one, there is no such a behavior, which is related to the lack of the ability to a proper periodicity detection for this map in this case. And here the second signal and the same results. And again, even though there is now some, let's say, desired behavior present in this first map, in the robust ones, it is just more visible and simply can be considered as better. Okay, so I also mentioned the performance indicator, and these are the plots of this indicator for different values of the parameters of the alpha stable distribution taken to the, let's say, to simulate a signal in this first model. And here we have the plots against different values of alpha. So of course, the lower the alpha, the more heavy the signal is, and the more extreme the task is to perform. And indeed, we can see that the performance of all maps drops with lower alpha. But what's important here is that here we have the result. This, let's say, the blue line is for the standard classical map. And here we can see that for non-Gaussian signals, so let's say in this area, it is clearly worse than the proposed robust methods. Here we would consider the Kendall and both trimmed estimator-based maps as the best ones. And similar story for different values of sigma. So for different values of the scale of the noise, now the larger the value of sigma, the more extreme the task is, because the noise, the background noise becomes more significant. And the same story here is that the blue line representing the sample autocorrelation function based map is just the worst among all the rest ones. And the similar comparison, but for the second signal, and now what we are changing is the amplitude of the added cyclic impulses, because let me remind you, there we added the impulses to the signal artificially. And here in the red ellipse, there is a case that was considered before, which I was presenting the plots before. And here we have some other values of these amplitudes added to the signal. And now the lower the amplitudes, the more extreme, more challenging the task is, because the periodicity becomes more hidden and harder to detect. And again, we can see that for these most extreme cases, the robust measures tend to perform better than the standard one. And the last thing here is the behavior of the map, but not for periodic signal with the periodicity included with them, but now for the non-periodic signal, because it turns out that it is also important to engineers to be able to assess the performance of the map when there is no periodicity present in the signal. So here, in such case, the map shouldn't bring any relevant information. It should be as homogeneous as possible and with as low values as possible, which again is the case for robust maps, especially for both Kendall and Spearman ones. And yet we can see that the behavior, especially for this classical map, is very similar to the one that I presented before for a cyclic signal, because of such a strong influence of the outlying values for this particular map. And a similar story for the second signal. There is no periodicity detected by all maps, which is correct because there is none in this case. But these maps, especially, are much more homogeneous and represent much more desired behavior of the map, because the values are very low and there are no significant disturbances present in the signal. Yet it is not the case for the standard one, because here the disturbances that were present here also for the periodic signal, they stay because they are coming from these outlying values present in the signal. To summarize, we presented the application of robust statistics to solve the periodicity detection task in context of local damage detection. And as we presented, the robust methods tends to be much more efficient for non-Gaussian signals than the standard methods. And such a behavior might be occurring in practice because of the behavior processes conducted by the machine. and some external conditions. And in the future, we plan to develop further the methodology and apply it to more data sets in such setup. This is the information about the project, which is for which this is the research is part for. Some references, including our paper submitted on this topic. And that's all. Thank you for your attention.